Welcome everybody to Lecture 4 of Environmental Science 347, Climatology. This time we'll look at the thermal response to the climate system, what that entails basically, understanding heat energy in the climate system, the global climate system, how it's measured and transferred in different places around the globe. How different areas of the world will cool and warm, how that related to the ultimate climate that they have today. And then the local radiation budgets, how they impact the climates of smaller areas. In other words, the inputs and outputs of localized energy into one particular spot and how that relates to the climate of any one particular spot across the globe. So we'll start with an understanding of what heat energy is. The driving question here, what are the causes and the consequences of heat energy transfer within the Earth system? And that is to say, how does heat energy move around the Earth? How do we measure it, and how does it yield a certain local climate? So let's distinguish between temperature and heat. Remembering from high school, I guess, that all matter is composed of atoms or molecules that are always in some kind of motion, in a vibrational state, a rotational state, or translational motion. They don't just sit still, with one exception, which we'll get to in a minute. And the energy is represented by what we call kinetic energy. And the temperature is directly related to that average kinetic energy of the atoms or the molecules composing a substance. These two examples being carbon dioxide and oxygen. Those molecules aren't static. They kind of pulse sometimes, they'll rotate, and they'll revolve a little bit from time to time. So they all have some kind of energy, and we relate temperature to the amount of energy that those molecules and sometimes atoms have. So to distinguish between temperature and heat, we look at the internal energy of a substance, which encompasses all the energy within that substance or chunk of matter, if you will. The heat is the energy transfer between systems or within components of a system, from place A to place B, if they're two separate systems, or if there's one conglomerate and it goes from one spot to the other. And the differences in the temperature across a lateral or horizontal surface, if you will govern the direction of heat transfer. I say horizontal in a two-dimensional surface, but obviously with Earth, that's a three-dimensional surface, so we have to think about it in the vertical as well. Just to revisit some of the temperature scales, the Celsius scale is the one that is by and large used in scientific studies, scientific literature. You're not going to hear Fahrenheit very much, and that's the classical 0 degrees C is freezing of water, 100 degrees C is the boiling of water. And technically, that's at sea level. One of the things you'll find out is that higher levels into the atmosphere, where the atmospheric pressure is not as great, water actually boils at a slightly lower temperature than 100 degrees Celsius. Fahrenheit's, of course, what we use here in the States, where the freezing point is 32 and the boiling point is 212, but the U.S. really one of the very few nations that kind of uses that scale for public reports. Talked a little bit about molecular motions. That's where we introduce absolute zero. That's the theoretical temperature which all that molecular motion stops. So when you think temperature is proportional to molecular motion, if the motion stops, we can't get below that. We can't get below that level. So that's what we call absolute zero. On the Celsius scale, that corresponds to minus 273.15. But we've also introduced the Kelvin scale. And that's where the temperature is measured in kelvins, technically not degree kelvins, just kelvins, above zero. And that's more of a direct measure of the average kinetic molecular activity. And because it starts with zero when there's no motion, as far as we know, we can't have negative motion, so there are no negative values. Everything is zero or above on the Kelvin scale. And this is just the overview of how some of these scales look in the classical liquid and glass thermometers. Boiling point of water, 212 Fahrenheit, 100 C, and 373.15 kelvins. The the interval between kelvins is the same as the interval between degrees Fahrenheit. In other words, to get kelvins, you just subtract off Celsius by 273.15. There's more of a different algebraic conversion to get from Celsius to Fahrenheit. Basically, you take Celsius times 1.8 and add 32, and then you get Fahrenheit. But that's easy to look up online. So when we think about another way to measure how much energy, in addition to just temperature and how molecules are moving, we think about how much energy we need to raise the temperature of something. And the metric system, it's the calorie. It's the quantity of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. So that's not a lot. You might still hear the term BTU thrown around, especially for home heating units, that type of thing. The British Thermal Unit, or BTU, that's the amount of heat equivalent required to raise the temperature of 1 pound of water 1 degree Fahrenheit. But calories is something that's really by and large used nowadays. To measure temperature, the old way, if you will, is the liquid and glass thermometer. It used to be mercury and glass thermometer, but most of those have switched now to alcohol, just colored alcohol in glass, because mercury is poisonous, and should it leak, that's a bad scene. But for most scientific purposes, the ones used in the National Weather Service offices, most weather sensors that we see for widespread dissemination of weather information, those are electronic. In other words, there's an electrical conductor with resistance, some kind of resistance, and that resistance changes with fluctuations in the temperature. So it's a very, very high correlation. So as we see a change in the electrical signal, we can easily correlate that to temperature. And that's how most temperatures are actually taken nowadays. Important to remember, and it's not as much of an issue nowadays with the electrical temperature sensors, but the old liquid and glass thermometers, they're not instantaneous. They take a little while to react. If the temperature suddenly drops, the thermometer is going to take more than just a couple of seconds to react. So important to remember the response or lag time at which the instrument resolves those changes in temperatures. Fortunately, that's not as much of an issue as we have today. So then, how is heat energy moved around the Earth system? Several ways. First, let's talk about those gradients in temperature. We talk about a temperature gradient a lot in both operational meteorology as well as in climate science. And here's what we mean by a gradient. We mean a change in temperature over a distance. That's the short version. How the temperature changes over a distance is called the temperature gradient. And heat or energy here does kind of move or flow in response to the second law of thermodynamics, which effectively says that heat energy is flowing from areas of high temperature to areas of low temperature. All right, we in the old days used to think of this as like caloric or some kind of ooze or ether, but it's not. It's energy. It's kind of moving from an area of high energy to a low energy state. So flowing from high to low. That's a good way to remember it using the rhyme. It flows from high to low. Go back to a couple lectures ago, we talked about a black body. A black body is a substance which absorbs all the radiation upon it in all parts of the electromagnetic spectrum and then emits all that energy once again. Not really reflecting, but absorbing it, reaching a temperature, and emitting it. So the temperature of that object never changes. It's consistent. Now, if you begin to absorb more radiation than you're giving off, you're going to be heating that object. All right, so we're not a black body anymore. We're just talking about any kind of physical entity. All right, absorbing more radiation than you're sending back, that's radiational heating. Conversely, the other way around. If something is emitting more radiation than it's bringing in, the temperature is going to drop. So we'll call that radiational cooling. You might have heard the term radiational cooling tossed around in weather forecasts a lot. that happens when we have, and it's mostly in the winter, when the sky is clear, there's not a lot of wind, it's kind of dry out, and the earth is cooling very, very quickly. And if we don't have a lot of clouds, we don't have a lot of water vapor in the atmosphere to kind of send energy back down to the system or send radiation back down to the ground, there is going to be a more rapid cooling versus if there were clouds, water vapor and the like up in the sky. Conduction is another important heat transfer process. Think about a pan on a stove. The things are in connection with one another. So it's the basic transfer of kinetic energy of the atoms and molecules via collisions from one thing to another. And it's generally a solid. I mean, it can happen with gases and liquids, but ideally we think about a solid. The effect or the strength, if you will, of how that energy is transferred between the two substances is called heat conductivity. The ratio of the rate of heat transport across an area, across that temperature gradient or that change in temperature across a lateral area. For this, think about metal and wood. If you've got to stir something in that pan, that cast iron pan on that stove, you may want to use a wooden spoon as opposed to a metal spoon, right? Because metal has a higher heat conductivity than wood, right? So if you put a metal spoon into that frying pan, the heat is going to go through that metal a lot easier than it would just putting a wooden spoon into that frying pan. So we say that the metal has a much higher heat conductivity than does wood. And this can be for liquids and gases too. We oftentimes think of it as solids because solids are just a much better conductor of heat versus liquids and gases. Here are a few examples of the conductivity. Copper, aluminum, iron, those are all fairly high, especially copper and aluminum. That's why you'll oftentimes hear about people trying to sell you copper and aluminum cookware, although I'm quite a fan of the cast iron myself. But look how dramatically those numbers drop off toward the bottom of that chart. Dry sand, air at 20 degrees C, air at 0 degrees C. These do not conduct heat at all very well. If you think about what we said at the beginning of the course, I said the sun doesn't heat the air very much. And this is evidence of that. Most of the heating of the air comes from the sun heating the ground and then the ground heating the air above it. So again, the air is not very conductive of heat. And by the way, that's one of the reasons why air that is dead, if you will, not moving, is a great insulator for things like coffee cups, coolers. To keep you basically have two layers with a bunch of dead air in between them because that air is not conducting heat. So whatever's the inside there is probably going to remain the same temperature. Convection, the third of these ways to move heat around, is the transport of heat within fluid motions of a substance and generally a fluid itself, not generally a solid. This is in fluids, which means liquid and gases. When we say fluids in science, we mean anything that flows, and that is a liquid or a gas. So be careful there. Don't get tripped up on the term fluids. That doesn't necessarily mean liquid. Anything that flows is a fluid, a liquid or a gas. Convection in the atmosphere largely happens from different density currents. And what we mean by that, if you've got very high heat, very high humidity, that starts to rise into a cooler atmosphere above it, so then it rises more quickly. Think back to a hot, humid day in June or July. You have hot air rising into a relatively cooler atmosphere. That's convection. If you turned on that stove and you didn't put a frying pan on top of it and just had the stove on, the air right over top of that heating element is going to get hot, and that's going to rise. Again, that's convection. So when you take convection and conduction together, those two things are called sensible heating. So conduction, convection together, the two C's give you sensible heating. And that's different from latent heating, which involves the change of phase of water. All right, so when you change the phase of water, That's a heat transfer process. The temperature, you have to add energy to change the temperature of water. Let's say we're starting with liquid, all right, and you want to boil it. Well, you've got to add energy to take the temperature up, add energy to take the temperature up, add energy to take the temperature up. Then it's ready to change to a vapor. So you go from liquid at 212, add energy, in Fahrenheit, liquid at 212 Fahrenheit, add energy to get it to a gas at 212 Fahrenheit. So making that change in phase requires the additional energy, even though the temperature doesn't change, as you go across that phase boundary, all right? So that's what we call latent heat, that quantity of heat involved in changing the phase of a substance. And for these purposes, we're talking mainly water, because that's what we're most curious about from an atmospheric science perspective. Water, because we don't see oxygen change in phases and nitrogen change in phases in the atmosphere. It's almost always a gas. Water vapor goes to liquid, goes to gas, goes to solid. It can exist in all three of those phases on the Earth. This diagram illustrates it a little bit better. If we start on the left side, that's cold, that's solid. You add heat to the system and you go from left to right. You melt to liquid and then you add more energy and you get evaporation to a vapor. There are some instances where you can skip the liquid phase altogether, go from solid to vapor. That's called sublimation. The reverse is also true. As things cool off very quickly, you can go from a vapor to a liquid. Again, you're removing energy, so the molecules are slowing down. They go from a gas to a liquid. Remove more energy out of the system, the molecules slow down, and then you go into a solid. They all line up into a pretty lattice, they slow down, and you have a solid, which is ice. And there are occasions with the right atmospheric conditions where you can go from a vapor right onto a solid. In fact, thinking back to that original thing, going from solid straight to vapor, if you've ever heard the term dry ice, that's frozen carbon dioxide that automatically goes to a vapor because the pressure in the atmosphere, in Earth's atmosphere, isn't high enough to allow it to exist in a liquid form. So it goes from straight solid to vapor. Again, that's just carbon dioxide. Carbon dioxide ice goes straight from solid to vapor, or it sublimates, thusly dry ice because it's never wet. Specific heat is related to the calorie. It's the amount of heat that will raise the temperature of 1 gram of a substance 1 degree Celsius. So, the calorie is 1 gram, 1 gram of water, 1 degree Celsius. But 1 gram of any substance by 1 Celsius is known as the specific heat. And by definition and convention, that is measured relative to liquid water, which comes in as a 1. But the variation in the specific heat from one substance to another implies and becomes kind of evident that different materials have different capacities for storing energy in terms of bringing in that energy and then giving it off. Think about if you cook and you have aluminum foil in the oven, you take whatever it is out of the oven, the aluminum foil cools off in a big hurry. Okay, it's a lot different than a cast iron pan if you take it out of the oven. You don't want to touch cast iron pan. Aluminum foil cools off much more quickly. And those give you changes, and those are related to differences in specific heat. And again, here's another table of that. So water, mud, especially wet mud, if you will, wood, aluminum, these are things that take more energy to raise the temperature and more energy to remove or cool to lower the temperature. It works both ways. And then down toward the bottom, you have things like copper, silver, and gold. It takes a lot less energy to raise those temperatures. And the reverse is true as well. It takes a lot less, to remove a lot less energy to let the temperatures drop. So thinking about that, there's this other term that's not really quantitative called thermal inertia. So it's the resistance to a change in temperature. So the input or output of equal amounts of heat energy causes a surface to warm or cool more than the equivalent surface of a body of water over a given span of time. What does this mean? This means is that land and water on the Earth's surface heat up at different rates. It takes a lot more energy through time to raise the temperature of the ocean versus raise the temperature of dry land. So another term for that is thermal inertia. There's more thermal inertia in the global oceans than there is the global land masses. And as a result, we see different climates in places on the Earth that are close to land versus close to oceans or massive lakes. These climates are broken down to two primary types: maritime, meaning near oceans, marine areas, and continental, which generally means in the middle of a continent, nowhere near any water. So marine climates, generally downwind of an ocean, and experience much less contrast in their temperatures through the course of a year, specifically between winter and summer. All right, there are variations, but because because there's that thermal inertia in the water, the temperature through the course of the year does not change as much. You don't have these wicked bad highs during the summer or wicked cold lows in the winter. Continental climates, you do get that. All right, well inland, and you get a much greater contrast between the hottest hot during the summer and the coldest cold during the winter. We see a little of that, what's going on right now, this being February of 2021, where there's this massive polar outbreak of the southern plains that's all the way down into Oklahoma and Texas. All right, Houston is typically more of a maritime climate, but because the wind has been howling from the north, it is dragging all of this polar air down the front range of the Rockies, down the plains, all the way down into Texas. Unusual, to say the least. But places farther north, like Kansas City, for example, St. Louis, Minneapolis, Denver, these are places that are continental climates. They're nowhere near any water, all right? So they have much bigger fluctuations in their temperatures during the course of a year. Seattle, Los Angeles, San Francisco, these places where the average wind direction through most of the year is coming from the west off the Pacific, those are maritime climates. They do have fluctuations, no question, but they are not as intense during the course of the year as continental climates. So with that in mind, what do these imbalances of heat energy mean for additional movement of heat around the Earth system? Well, let's go into this graphic real quick. This is a little bit complicated, but let's take a couple of very important points from this. When we look at the atmosphere versus the surface, the ground itself, how incoming solar radiation is intercepted by the Earth and interacts with the Earth regarding the Earth's atmosphere and the surface. And these are global annual averages. Toward the top left there is the incoming solar radiation, and that's scaled to 100. So 100%. As we said a couple of lectures ago, lots of things happen to that incoming solar radiation as it enters the top of the atmosphere. It can be backscattered, it can be reflected by the clouds, reflected by the time it gets to the surface, absorbed by water vapor in the atmosphere, or absorbed by clouds, which are also liquid water as well as water vapor. But about half, 49%, about half of the incoming solar radiation gets to the ground. The rest of it is either scattered or absorbed. All right. And then the Earth is giving off some of that energy back, if you will. And to scale, that's 114. All right. And again, we're scaling it to 100. So it's actually a little bit more in the infrared than is coming in from the incoming solar. But you see the 114, that little curve goes to 105. Most of the energy given off from the ground, from the Earth's surface, as it goes back up into the atmosphere, is then absorbed by clouds, water vapor, carbon dioxide, or oxygen. Very little of that energy that's coming off of the ground, radiation, goes all the way up, back out of the atmosphere. Only about 9 units out of 114. We still have other things going on in the atmosphere. The CO2, the oxygen, they're emitting back out in a long wave IR. The clouds that are already there, they're sending back infrared radiation back out in space, as well as sending some back down to the ground as well. And then there are those heat fluxes, the sensible heat fluxes, the latent heat fluxes, the conduction, the convection, that latent heat where we're changing the phases, those leaving the ground as well. But the most important thing is to remember, half of the incoming solar radiation gets to the ground. And then most of the infrared radiation leaving the Earth's surface is absorbed by the atmosphere. If you want to get deep into the weeds, you can get into the calculations here. But the point being is that, is what I said before, there's most of the IR, infrared, leaving the Earth's surface is absorbed and then emitted by the atmosphere. So back to the latent heating thing, when we look at the atmosphere versus the Earth's surface, that transfer of the heat energy from one place to another as a consequence of the phase changes of water is transferred from the Earth's surface to the troposphere through that latent heating. So what do we mean by that? Huge amounts of heat are required to bring about the phase changes of water compared to phase changes of other naturally occurring substances. There is a boatload of energy, all right, into the atmosphere, taken into the atmosphere by latent heating, right? Because it takes energy to evaporate any kind of liquid on the ground, any kind of soil moisture, and then send it into the atmosphere. It rises. When it cools and forms clouds, we're going from the gas to the liquid. That releases energy into the atmosphere, all right, because the water is dropping its energy state from a vapor to a liquid. So that's getting cooler, meaning there's a release of heat energy into the atmosphere. So that's what latent heating is all about. So that happens a lot, all right? This graphic I think is kind of interesting. It's a percentage of annual precipitation that falls on land that originates as water that vaporized from the continents. In other words, places that rain or snow fell. Where did that water originate? All right, and those reds and yellows shows you that water originated on the land, meaning soil moisture or maybe a lake, as opposed to that water came in from like the Gulf of Mexico or the Atlantic Ocean or the Pacific Ocean, like that. And what you see is one of the things that I think is very interesting there is Central Asia, where you've got anything from the Himalayas northward, and then there's that area in the upper plains in North America. But you see the blue areas and purple areas along the Gulf Coast, the U.S., and certainly along the northwest coast of North America. All their water's coming in from the Pacific Ocean, not coming from the land that the atmosphere is over top of. This kind of harkens back a little bit to sum up what we said before about moving energy from the Earth's surface. So thinking about how the Earth's surface cools from left to right there. One is the vaporization of water. The net emission of infrared radiation, in other words, just giving off energy. And then conduction plus convection, right? Those currents, all right? So those are the three things that are cooling the Earth's surface. And then remembering how much energy it does take to change the phase of water from a liquid to a gas, or from a liquid to a solid, removing energy. To emphasize the point that we had before, is that you can increase the heat, or you can increase the temperature by adding heat to water. Let's say it's, we'll take the higher end here. Let's say you want to change water to vapor, 93 degrees C, 94 degrees C, 95, all the way to 100. You have to keep adding energy to get it to jump from liquid at 100 C to a vapor at 100 C. It takes a big jump in energy. Right? It doesn't just flip and it's there. Right? It takes energy to go through that phase change and then to resume raising the temperature. Two nicknames for these phase changes: latent heat of fusion, so that's the amount of heat required to convert the solid at its melting point to the liquid without the temperature actually changing. All right, so in other words, I'm going from 0 C ice to 0 C liquid water without a change in temperature. I still had to add energy, even though the temperature didn't change, had to add energy to the system to get the phase to change. At the higher end, that's that latent heat of vaporization, the amount of heat required to convert from liquid to a gas. All right, I'm going from water that's 100 degrees Celsius to a gas that's 100 degrees Celsius. I didn't change the temperature, but I had to add energy. I had to add heat to get that phase to change. And that's what those two terms are all about. Sensible heating is what we said before: conduction and convection. All right. Latent kind of means it's hidden heat. Right? Where sensible heat is obvious. You're moving heat around through conduction or convection directly, sensibly. This combines with the latent heating, all right, to channel heat from the Earth's surface up into the troposphere. Remember, all the weather happens in the troposphere, basically the bottom 10 miles of the atmosphere. So then how do these imbalances play into local climatologies? What determines the climatology of a specific location? All right, go back to think what we discussed a couple of lectures ago regarding where you are on the planet regarding latitude. I mean, that's a huge, huge thing, just like you remember from grade school. All right, over the equator, or those areas between the Tropic of Cancer and the Tropic of Capricorn, the sun's rays are more direct over a narrow area, over a smaller physical area. Toward the poles, you've got the same energy spread over a broader area, so you're getting less energy per unit area. No surprise, it's going to be a little colder at the poles just from those arguments, all right? So when you look at that, and also look at things like ocean circulation, how air masses move around, how storm systems move around, you get a surplus of heat energy, surprise, surprise, near the equator, and a deficit at the poles. So the poles end up being colder and the equator ends up being warmer. So what do we mean by air masses? An air mass exchange is where one air mass bumps up into another and you've got a mixing. All right? An air mass is a huge volume of air that covers thousands of square kilometers, square miles, that is relatively uniform in temperature and humidity. And the properties of that air mass largely depend on what's immediately below it. So if you have the air that's sitting over Alaska, central Alaska, it's sitting over north central Canada for a couple of days and there's a whole bunch of snow, that stuff gets cold. Similarly, if you've got a chunk of air that's sitting over the central part of the Pacific Ocean near the equator, that gets warm and it gets humid because you're over top of the ocean. Looking at North America, these are the source regions of many of these air masses. And they fall into four basic classes, kind of a matrix this way. You've got continental, polar. Continental means it originates over the continent, so it's dry. And polar meaning it's cold. Makes sense. Now there's maritime polar, maritime water, meaning it's wet and cold. It has a source region over the North Atlantic or North Pacific. So they're wet and cold. And then in the warm versions, there's maritime tropical, all right, and that's, it's over tropical ocean waters, right? But be careful here. There's also continental tropical. We're very used to just in the lexicon saying tropical, meaning hot and humid. But that's not necessarily the case here. When we say continental tropical, we're talking about tropical as more of a directional thing. It started in the tropics, but It's continental in origin, which means it's dry. It is a hot, dry air mass. Think Phoenix. Think the Sahara. It's hot. It came from the tropics, but it's hot and dry. All right, so those are the big four. To the top, you see something that's called Arctic air mass, which is just crazy cold. And when it's that cold, there's almost no moisture in it anyway because it's too cold. Very cold air does not have much water in it at all. So the big four: continental polar, maritime polar, continental tropical, maritime tropical. Another way to move the heat in these bigger fashions is through storm movement. Latent heat in storms moving away from the equator is moving heat away from the hot spot, moving it from the equator toward the poles. And it can go equator north or equator south. Hurricanes, tropical storms, they're the same physical entity, basically. They're well known for doing this. They have tremendous amounts of that latent heat because you're evaporating warm water off of the ocean, throwing it up into the atmosphere, and then turning it into liquid, releasing tremendous amounts of heat back into the atmosphere. So as those things move toward the poles, away from the tropics, they're bringing a phenomenal amount of heat with them. The other thing, when we think about moving heat around, especially away from the tropical areas toward the higher latitudes, the middle latitudes of the Earth, we think about ocean circulation. They contribute to heat transport from the warm tropics to the cooler latitudes because we've got large areas of high pressure that are over the oceans. That wind puts a little stress on the ocean. And because the Earth turns, we have kind of a movement of the water below and at the surface as well that move the ocean waters around in these ocean currents. The most famous one, at least here on the east coast of the U.S., is called the Gulf Stream. I'll show you a little picture of that in a moment. But remember, when we talk about the interaction between the ocean and the air immediately above it, water that is warmer than the air above it is a heat source from the atmosphere. Remember that it goes from high to low. So if the water is warmer, let's say it's 70 degrees, than the air, 50 degrees, there's a net flux, if you will, or an exchange of heat toward the atmosphere. It's a heat source. Reverse is true. If your air is 70 degrees and your water is 50, that is a heat sink for the atmosphere. That heat energy is basically migrating into the water. The Gulf Stream, kind of shown here, if you look at the oranges and yellows, see how they curl up the east coast of Florida, back off the coast of North Carolina, and then that yellow ribbon, if you will, goes into the North Atlantic. That's the Gulf Stream current, and that's part of a much larger thermohaline circulation. Density, which means temperature, and salinity, saltiness, currents that are driven by this movement of these water masses going all around the ocean basins, the Atlantic, the Pacific, the Indian, the Antarctic, the Southern Ocean, all right, because we've got different water temperatures, we've got different water salinities, and the Earth is turning, and it bumps into continents. We develop different ocean circulations and ocean currents. And this whole thing together is known as the meridional overturning circulation. You can think of it as the MOC, the thermohaline circulation, but this is part of a grander ocean circulation that goes across the whole Earth. But for our purposes here on the East Coast, the Gulf Stream, what you see there in the orange and yellow, is the most important. So then what is controlling the local temperature during the course of the year and over the course of the daytime hours? All right, so first let's look at the local radiation budget. Think back to the latitude. All right, how much solar are we getting during the day anyway? But then when we think about the ground temperature, the highs and the lows for the day, you got to think about the cloud cover and what is the ground made out of? Are we over the ocean? Are we over the land? And in fact, what's on the land? Is it forested? Is it paved over? Is it concrete? Is it suburban? What's the land made of? All those things matter when we look at what the local temperature is. Two other ways to look at this back at the latitude, these latitude arguments. Or the top is Fairbanks, Alaska. The bottom one is Ghana and Guam. So let's walk through this real quick because it's a little weird. All right, but on the top graphic on the vertical axis is the hour of the day. 0 at the bottom being midnight, up to 12 is noon, then 24, midnight again. So going through the day from bottom to up. Then going horizontally is the month of the year. So January through June in the middle, and then December at the end. So at Fairbanks, Alaska, at a very high latitude, the temperature, which is color-coded here, all right, changes a lot during the course of the year because of the solar changes. You get a lot more sun in the summer than you're getting in the winter at that latitude. So you see this big maximum there right in the middle in June, July, August, where you've got most of the solar energy. So that's where it's warmest. And frankly, it's quite cold, as you might imagine, in the middle of Alaska in the winter. But in Guam, it's different. At 13 degrees north latitude, you're getting a lot of sun every day, all year long. So you don't have those big fluctuations that you have in a place like Alaska. You have fluctuations from day to night, but you don't have them during the course of the year. In other words, the top one, you see most of those lines vertically. The temperature contours, if you will, show big differences in the temperatures during the course of the year. The temperatures during day to night, they change, but not as much. Whereas a place like Guam in the tropics, which gets a lot of sun all the time during the daylight hours, the biggest changes of temperature don't necessarily occur over the course of the year. There are bigger changes from day to night, because you see that during the daylight hours, it's almost always sometimes between about 78 and 84. And you can hardly say that about Fairbanks, Alaska. Look at this another way. We look at the average monthly temperature here on the vertical axis, and then on the horizontal axis through time, January through December, through the course of the year. That top flat line is Manaus, Brazil, very close to the equator, 3.13 degrees south latitude. There's almost no change at all in the monthly average temperature. Kansas City, continental climate here in the United States, obviously there is a temperature. January, December, it's lower. June, July, it's higher. All right. But then you go into the Northwest Territories, Canada, and Yellowknife, you have that fluctuation, but it's a bigger fluctuation during the course of the year because you have much bigger changes in the amount of incoming solar radiation during the course of a year than you do in a Kansas City and certainly in Brazil. Because the other thing is that the sun is out longer in June and July in Yellowknife than it is in Brazil, Manaus. You still only have about 12 hours of daylight all year long in Brazil. In Yellowknife, Canada, during the dead of winter, there's only a few hours of sunlight a day. And then during the summer, even though the sun doesn't get as high, the sun is still up for 19 or 20 hours. So you get a lot more sun. And that matters. So when we think about the seasons, when we do climate and we do meteorology, it's a little different than the classical astronomical seasons that you're brought up with. Where we say spring is on March 21st. That's certainly astronomical spring. That's when the sun is giving everybody 12 hours of daylight, as it were. But to figure out temperature swings, temperature patterns, in meteorology, climatology, we define the seasons as the hottest and coolest months of the year. So the three hottest months of the year least in the northern hemisphere, are June, July, and August. The 3 coldest months of the year, again, northern hemisphere, December, January, and February. Remember that December, January, and February are summer in Australia, right? So you take those months in between and you get spring and fall. One of the other things I like to remind people is why the hottest time of the day is not at noon when the sun is the highest in the sky. And this is a complicated graph, but one worth walking through. All right, so the red line at the top is the air temperature. And the specific number isn't as important. We're just talking about the trend here. Starting from midnight to noon and then to midnight again. The temperature is dropping till about sunrise. Then it rises through the afternoon and then starts to drop late in the afternoon and through the night. Well, why is that? Why is it not right at noon? Well, the sun, shown by the green line here, comes up at 6, peaks at noon, and then sets at 6. So that shows you how much energy is coming in from the sun. All right, so it makes sense that things are cooling from midnight to 6 because the sun's not out. All right. The Earth is giving up radiation, so it's cooling. And that's the terrestrial irradiation. So that makes sense. Midnight to 6, the red and the blue lines are kind of chugging along at the same rate. Then the sun comes up at 6, boom. And suddenly there is a tremendous amount of solar radiation coming in, going up dramatically and quickly, peaking at noon. So you start to heat the ground very rapidly. So with the ground temperature going up, it's also starting to send more terrestrial radiation back up because it's now hotter. Ground is now hotter, so that's starting to give off more energy, okay, than it did 3 or 4 in the morning. So you've got more and more incoming solar, and you've got outgoing Earth or terrestrial radiation, right? So the temperature continues to rise until a little bit after noon, because it's only after noon that those curves cross again. In other words, noon, 1, 2 o'clock, there is still more energy coming in from the sun than is going out from the Earth. You know, the Earth can't cool fast enough. There's still too much sun coming in, even past noon. Once we get past about noon or 3, depending on what the season is, the sun is starting to get lower in the sky, where the atmosphere can begin, or the ground, can start to cool off again. And then the temperature will slowly begin to drop. All right? So noon, 1, 2, there is still more solar coming in than terrestrial cooling going on. And it's only after the sun starts to get lower in the sky again that the ground can catch up and cool off enough where the temperature begins to drop. And then obviously once the sun goes down, you see much more rapid cooling taking place. But that's why the hottest part of the day is at noon. We think about other things that are controlling the temperature in addition to what we just said. Think about what the ground is made of. We think about a dry surface or a wet surface. Is it pavement? Is it vegetated? All of those things matter. All else being equal, because what we said before, it takes a lot more energy to raise the temperature of water than it does raise the temperature of dry ground. If you have solar energy coming in, it's going to heat a dry ground a lot more than a moist or vegetated surface, because that energy can go more into raising the temperature of a dry ground as opposed to that energy going into trying to evaporate water or raise temperature of a moist soil. Same energy is coming in, but if it's a dry surface, that energy doesn't have to be wasted, if you will, into trying to evaporate water or into raising the temperature of water. All right? If there's no water, then all that energy can go boom right into heating up the land. So dry land is going to warm up way more than moist land, and certainly more than water. And a vegetated surface largely is in areas that are moist. We do think about snow, especially this time of year. Snow has a very high albedo or reflectivity and dramatically reduces the amount of incoming solar that is absorbed and converted to heat. It's very reflective in the visible part of the spectrum. So as a result, the air over top of it isn't going to get as warm. And that's going to lower the maximum temperature for the day. The other thing to remember, though, is while snow is very reflective and solar and visible, it's actually very emissive in the infrared part of the spectrum, meaning it gives up energy very, very quickly. So when the sun goes down, it gets really cold near snowpack. I mean, colder than just 32. It's continuing to give up energy. So some of the coldest nights you can have are, especially here where we live in the middle latitudes, are a clear night with no wind right after the snow stops falling and there's a fresh snowpack on the ground. Because you're giving up a lot of energy from the surface very quickly, and with no cloud cover, not a lot of water vapor in the atmosphere, there's nothing to kind of send energy back. So some of the coldest air you're going to have, coldest local nights you're going to have, clear sky, calm winds, fresh snowpack. Another important way temperature changes, this is called a temperature advection. And this is actually what's going on in Texas here in February. Arrow A right now. It is dragging cold air basically out of Canada, out from the poles. Actually, this stuff started in Siberia, all the way down the front range of the Rockies and into the southern plains. The cold air has to come from somewhere. I mean, Texas just doesn't up and get cold all by itself. The cold air has to come from somewhere, and that's cold air advection. Dragging in the cold air from somewhere else through winds blowing it there is called cold advection. The reverse is true. You can have warm air advection. And this happens, and is not uncommon to see this in the dead of winter. Here in the middle Atlantic, when warm advection kicks in, it can kick in after nightfall, and the temperature will rise during the night, which seems really counterintuitive. But a cloudy night and the wind kicks in from the southwest, your temperature can climb several degrees in the middle of the night. Right? So warm air advection occurs when the wind is bringing in warmer air from somewhere else. So that's a big deal too. Important also to remember that air it's not all two-dimensional. Air also moves vertically. That's a big deal in mountainous areas or places immediately downwind of mountainous areas like Lynchburg, Richmond, Washington, Fredericksburg, Baltimore, Philadelphia, all these places immediately eastward from the Appalachians. Some of that cold air will come down the eastern side of the Appalachians and warm up a little bit. Because as you take air down, it warms. That's why we have ski resorts in the mountains, because you take air up, it gets cold. You take air down, it gets warm. All right. This is part of the reason that the nastiest cold air is staying on the other side of the Appalachian Mountains. And while it's certainly cold, it's not brutal cold like it is between the Rockies and the Appalachians right now. Look on a map, and again, this is February 15th, 2021. You go back and look at a map. Where's that cold air? It sits on the eastern side of the Rockies and the western side of the Appalachians. One final thing when we look at what's going on regarding the temperature at any one spot and what's the ground made out of, we have to look at the anthropogenic, man-made influence and the urban heat island effect. That's an area in urban centers where the air temperature is going to be higher compared to 15, 20 miles outside of town, because you've got more concrete, you've got more pavement, you've got more things like that, which send the heat back up into the atmosphere at night. Way more than they do out to the countryside, where you've still got plants and trees and forests. So things in the cities get a lot hotter during the day Concrete pavement, they're absorbing that heat and they give it back at night. Whereas out in the countryside, they haven't absorbed as much heat, so not giving much as much back at night. So it's kind of intuitive. Urban heat island, it gets hotter in the city, so it stays hotter at night. This is a map of New York in the thermal infrared. Just kind of shows you that idea. The urban heat islands result from a lack of moisture, lots of heat surfaces, lower albedo. And think about pavement. Pavement is black. It gets hot. And the biggest impact of these is when it's nighttime, the air is clear, and there's not much wind. Sky is clear and there's not much wind. All right. When it's cloudy and windy, again, we got clouds that the water vapor, they're sending infrared back down to the ground, and you've got a nice breeze. It kind of keeps the atmosphere much better mixed. But if you've got not a lot of wind and a clear sky, and the atmosphere isn't mixing much horizontally, that place in the countryside is easily going to be colder 10, 11, 12 o'clock at night than the city. No matter what city that is. All right, so that's the lecture. A little overview of temperature and how it relates to different climates globally and locally. So we'll have probably another homework set coming up a little bit later on, but not so much this week. Next week, we will talk more about the role of water in the climate system. We talked a touch about that with latent heat this lecture, but we'll get a lot more into the role of water, read precipitation in the climate system next time.